Hi, my name is Srini, and I'm a PhD candidate at the University of Maryland, Baltimore County. The title of the work that I'm going to be presenting today is CogAx, Early Assessment of Cognitive and Functional Impairment from Accelerometry. This work is a collaborative work with Soumyajit, Elizabeth, Arya, Dilmaria, Pivas, and Sandeep from University of Maryland, Baltimore County, University of Maryland, Baltimore, and the Indian Institute of Technology, Kharagpur. Activities can be broadly classified as simple and complex based on the complexity in the activity patterns. For instance, walking activity comprise of repetitive, similarly looking gestures, whereas eating comprises of multiple simple and complex activities. This makes recognizing complex activities a challenging problem. In activity recognition, multiple devices such as smartphones, watches, eyewear, sensors such as cameras, accelerometers, gyroscopes have found its application in various domains such as fitness tracking, fall detection, sports analytics, cognitive and physiological health assessment. Our work in particular falls under the category of cognitive and physiological health assessment. A disease in particular that is of interest to us is the Alzheimer's disease. Alzheimer's disease is a progressive disease of the brain that slowly causes impairment in memory and cognitive function. And it occurs when proteins called plaques and fibers called tangles build up in the brain and block nerve signals and destroy nerve cells. Dementia is a group of symptoms that affects mental cognitive tasks such as memory and reasoning. Alzheimer's disease kills more people than breast cancer and prostate cancer put together, and early detection of Alzheimer's disease helps save trillions of dollars. The symptoms of Alzheimer's includes confusion with time or place, trouble following conversation, misplacing things, changes in mood or personality, memory loss, and trouble with performing familiar tasks. This implies that the cognitive impairment is characterized by functional and behavioral changes. Currently, clinically diagnosing dementia involves extensive physical and laboratory tests, neurological exams, cognitive tests, and sometimes experimental imaging studies. Especially for older adults, going through these tests involve multiple hospital visits with long wait times and would be expensive to just diagnose the disease. Once the disease is diagnosed, plenty of time would help both clinicians and the individuals. It would help individuals to prepare a course of intervention, and it would help the individuals to prepare themselves psychologically. By availing early assessment, one can explore treatment options to mitigate the symptoms before it is too late, enroll in experimental clinical trials, adopt new lifestyle changes to improve the quality of living, and exponentially reduce the costs of treatments. A general tendency of individuals is to conceal symptoms as they lack insight and often hide their symptoms, leading to underdiagnosis of cognitive impairment. Passively assessing health using inexpensive and efficient wearables could help avoid underdiagnosis and would help promote hospital visit at an earlier stage. Keeping this in mind, the objective of this work is to enable early assessment of functional and cognitive health impairment through an individual's daily activities, captured through a simple accelerometer. Several literature exists that performs health assessment through activities. The first work that we show here involves computing handcrafted features such as interruptions in performing an activity, changing the sequence in performing the activities, parallelly performing different activities, and the duration of performing an activity. The authors proposed an unsupervised scoring method to detect the stage of dementia from ambient sensors. The second work that we show here follows a similar approach. However, the authors included accelerometer, electrodermal activity, and heart rate data into consideration. The more recent work uses both environmental sensors and mobile-based sensors with continuous data. And they extract features from each of these data modalities and use separate shallow learning models to extract those features, and they call the features as behaviorames. The authors fused the behavioromes together using another shallow learning model to predict the health assessment scores. The limitation of this work involves computing handcrafted features and having multiple steps of training that is really expensive in training a model. In our work, we plan to use a simple accelerometer sensor and propose an end-to-end pipeline to estimate the clinical scores without using any handcrafted features. Some of the challenges we experience in assessing health using activity data include marginal separability of data. From the figure, we observe that the data points overlap on each other, and the overlapping becomes more complex as the number of activities increases. We encounter these challenges as there can be multiple ways in which one can perform an activity. Also, there can be many ways in performing the same activity. Another challenge that exists is imbalance in the dataset. We encounter this challenge as we perform some activities, such as brushing teeth once or twice a day, but perform some activities many times a day, such as cooking, sweeping, and walking. To study the relationship between the activities and an underlying health impairment, we propose CogAx pipeline, which has 3 modules. The CogAx pipeline feeds on accelerometer data, and the raw windowed data with an overlap is fed to the contrastive learning module. The role of the contrastive learning module is to learn the representations that are closer to each other when the data instances belong to the same class and farther away from each other when they belong to different classes. These representations are then fed to the multitask learning framework, which has task-specific layers that determine the probability of a data instance belonging to a certain class. The multitask learning module enables us to learn both activity label and functional and cognitive impairment labels simultaneously. The estimated labels, along with the information if they were correctly classified or incorrectly classified, are fed to the modeling error module, where we compute an impairment indicator that is capable to highlighting changes in health impairment status. Let us now discuss the 3 modules in detail. Let us assume 2 data instances belonging to the same class, which is using toothbrush. As we can see here, in the first scenario, the person is brushing using an electric toothbrush, while in the second case, the person is using a traditional toothbrush. So essentially, the same activity is performed differently in 2 different ways. Typically, in a machine learning model, these types of data instances are misclassified and contribute to the model error. To avoid misclassifying such data instances, we propose to use contrastive learning. The 2 data instances are passed into the shared encoder layers to obtain the representations. To bring the 2 data instances closer together in the representation space, we maximize the mutual information between them. We achieve this by maximizing cosine similarity or max margin between the 2 representations. We maximize the mutual information for positive pair of data instances, as in this case, where the 2 data instances belong to the same class, that is brushing teeth. And we minimize the mutual information when the data instances belong to different classes. Here we show the flowchart after combining the contrastive learning module and multitask learning module. The representations learned by the contrastive learning module is fed to the task-specific layers to obtain the class labels for both primary and auxiliary tasks. Henceforth, the primary task will be abbreviated as PT, and auxiliary task will be abbreviated as AT. An interesting point to observe is that the contrastive learning uses the primary task labels. That means the representations are clustered together based on the primary task labels. Interestingly, we observed that concurrently learning 2 tasks induces a contrastive behavior on the auxiliary task labels as well. To optimize the proposed contrastive multitask learning model, we proposed to optimize 3 losses: contrastive loss to learn the representations the way we want, categorical cross entropy loss to learn both primary task labels and the auxiliary task labels. The contrastive loss is computed similar to a logistic regression loss function to maximize the similarity between the representations. The primary task loss is the sum of contrastive loss and the categorical cross entropy loss of the primary class classification. The auxiliary task loss is only a categorical cross entropy loss, as the contrastive loss of the primary task automatically induces contrastive effect onto the auxiliary task. Once we obtain the primary task and auxiliary task class labels, we feed those along with their corresponding true labels into the modeling error module, where we compute the impairment indicator. Impairment indicator can be defined as the misdetection of primary task labels when the auxiliary task labels are correctly classified. When we defined the losses, we observed that the contrastive multitask learning model favors estimating the activity labels better due to multiple losses involved in its computation. So we hypothesize that any misdetection in activity labels, in spite of this biased supervision, is due to the underlying health impairment. And we captured those missed detections as impairment indicator. To evaluate the CogAx pipeline, we consider two objectives. In objective 1, we study the relationship between activities and the functional impairment assessment, where the primary task label is activities and the auxiliary task label is activity performance score. And in objective 2, we study the relationship between activities and the cognitive impairment assessment, where the primary task is again activities and the auxiliary task is the stages of dementia. To evaluate the CogAx pipeline, we used two types of data, sensor-based and survey-based. We used accelerometer data from a wearable sensor known as Empatica E4 and captured activity data at 32 Hz while performing activities. Concurrently, we performed a series of clinical tests to assess their dementia status. Activity performance evaluation for activities of daily living, which are usually simple activities, and instrumental activities of daily living, which are mostly complex activities. We collected additional data such as electrodermal activity, photoplethysmography, and anxiety scale, and so on, but those data were not used in the study. The inclusion criteria to participate in the data collection effort was to at least be of 35 years of age and experience symptoms of dementia or any underlying neurodegenerative disorder. We collected survey and sensor-based data from 25 older adults who lived in a continuing care retirement facility. Here, we show the labels that were considered for both the objectives for primary and auxiliary task classification. The activity labels were provided by two annotators. The labels that were in agreement were chosen as the final labels. For objective 1 auxiliary task, the class labels ranges from 0 to 8 and were obtained from Barthel and Lawton scales from the survey-based clinical evaluation. Similarly, the auxiliary task labels for objective 2 are stages of dementia obtained from the slums examination, and the labels are normal control, mild cognitive impairment, and dementia. An interesting point to note here is that the auxiliary task labels for objective 1 were annotated at an activity level granularity. That is, the person can have unique score for each of the activities they perform. On the contrary, the auxiliary task labels for the objective 2 were annotated at a subject level granularity, meaning a person has the same dementia status irrespective of what and how they perform each activity. The CogAx pipeline has shared encoders that comprise of convolutional and fully connected layers. The output of the shared layers are fed to the task-specific layers that are fully connected layers. Since the number of classes for each objective and the task is different, it is reflected in the number of neurons of the final fully connected layer. Here we show the individual losses, that is contrastive loss, categorical cross entropy loss for the primary task, and the categorical cross entropy loss for the auxiliary task. And we also show the total loss. We observe that the contrastive loss converges slower than the categorical cross entropy losses. The categorical cross entropy losses aids in the quicker convergence of the contrastive loss and thus helps in the convergence of the entire CogAx model quicker. We now show the visualization of the representations learned by the shared layers. The figures to the left are color-coded based on the activity labels, and the figure on the right are color-coded based on the auxiliary task health impairment labels for both objectives. For the figures on the left, it is natural that the representations are grouped together if they belong to the same class due to the effect of contrastive loss computed based on the primary task labels. However, the figures on the right also exhibit the contrastive effect without explicitly applying a contrastive loss computed using auxiliary task labels. In these figures, we show the probability density function of the similarity between a medoid of the representations and the rest of the representations for correctly detected data instances versus the incorrectly detected data instances. We observe that the probability density function of the incorrectly detected data instances peaks at a lower value compared to that of the correctly detected data instances. This suggests that the missed detected data instances are farther away from the cluster centers for every activity. These misdetected activities are captured by our proposed impairment indicator, and we believe are caused due to the underlying health impairment. Next, we show the impairment indicator for the functional impairment assessment. As the performance scores decreases, the impairment indicator increases. The scores closer to 0 suggests that the individual becomes more independent, and we were able to capture those using the proposed impairment indicator. Similarly, we show the impairment indicator for the cognitive impairment assessment. We observe that the stage of dementia changes from normal to NCI. The model starts to misdetect, whereas as the stage changes from NCI to dementia, the impairment indicator reduces. We were able to relate these misdetections associated with MCI to our experience during the data collection effort. And we observed that individuals living with mild cognitive impairment were more confused, had trouble following orders, and were creative in improvising the activity routine. Finally, to show the association between the correctly detected primary task labels and auxiliary task labels, we use Kendall-Tau hypothesis testing. A null hypothesis here is that there is no association between the correctly detected primary task labels and auxiliary task labels. The tau values were obtained with a p-value less than 0.05, indicating that the null hypothesis can be rejected. A higher value of the tau coefficient suggests that there is high association between the correctly detected primary task labels and the auxiliary task labels. One of the limitations of our work is that the computations of the impairment indicator is done in a supervised manner. That means it requires the ground truth. The second limitation is that the impairment indicator does not consider the symptoms can be manifested through different activities for different individuals. In the future, we plan on mitigating these limitations and improve impairment indicator that can be personalized to each individual and computed in an unsupervised manner. In this work, we were able to study the relationship between activities and underlying functional and cognitive impairment using the accelerometer data and a novel contrastive multitask learning approach. Besides, By analyzing the model errors, we were able to quantify the errors and associated them with the underlying health impairment. Thank you so much for listening to my talk, and please feel free to contact us if you are curious about our work.